Welcome to this special episode of Frequency Matters, the RF and Microwave Update series. I'm Pat Hendo, and today I'm talking to Zeno Galchev, Marketing Director for MEMS Inertial Sensor Group at Analog Devices. Welcome, Zeno.
Thanks, Patrick. Thanks for having me.
So let's talk about an important technology related to microwave systems. What are MEMS and IMUs, and how are they used in relation to microwave systems?
So MEMS stands for Micro Electromechanical Systems, and they're micro machines, silicon mechanical beams, and resonators that can move and respond to inertial forces. So they're merged together with a signal processing ASIC. And then in an IMU, we have multiple MEMS inertial sensors to sense along typically 6 degrees of freedom, 3 axes of linear acceleration, which require accelerometers, and 3 axes of angular rate sensing, which require gyroscopes. Now, by having 6 degrees of freedom, you can orient a body within any 3-dimensional reference frame if you know the initial orientation. And with our IMUs, we go beyond providing the raw sensor readings. Sensors have many error sources, and we calibrate our IMUs over temperature and remove any observable errors that, to the extent that we can observe them, things like offset variation over temperature, sensitivity variation over temperature, alignment between the sensors and package, and other things. And so in this way, we can deliver a ready-to-use, environmentally aware sensor to our customers that offers the best possible accuracy and easy integration into their end system.
And so why would a microwave system need an IMU?
So, the primary function of an IMU and a microwave communication system is to provide feedback sensing on antenna stabilization systems, such as a horn antenna or on a gimbal or in a beam-forming phase array. And this is especially common in airborne, ground-based, surface, marine-type vehicles. So whereas, as I understand it, the alignment of an antenna's primary lobe has a direct impact on the receiver's signal strength, which directly then impacts the communication reliability, data rates, and even the power requirements of the transmission site. So in essence, it's very similar to the concept of image stabilization on cameras or optical sensing systems.
And so how would one choose what IMU to use with their microwave system?
Good question. So, one has to really consider the mission profile and accuracy requirements of their system. For antenna positioning, the first thing to consider is, of course, the accuracy of alignment that has to be met. This will determine the noise and sensitivity requirements. Next, you start to add the error contributors such as offset drift, nonlinearity, sensitivity accuracy, misalignment error, and other things. And then, because a lot of these are mobile platforms, one has to consider the dynamic error sources, such as broadband vibration that might exist in some of these applications. And this will typically lead to an offset change in accelerometers. This is known as vibration rectification error. And it will also lead to rate error and offset change in gyroscopes as well. And that's known as linear G sensitivity and vibration rectification. And actually, I might add, this is one area where Analog Devices excels and offers industry-leading vibration rejection and minimum VRE in our sensors. So this is this leads to a reduction in one of the primary error sources in dynamic systems.
Yeah, Analog Devices has been doing MEMS devices for a long, long time, so a lot of experience there. And so you just released a new product, the ADIS 16545. What's so special about this particular IMU?
Yeah, so as you said, now we have a 30-year history of inertial sensors. We started with very simple high G shock sensors that are used even today to deploy airbags in cars. We then moved to these kind of consumer sensors, where in the early phones would be used to orient the screen. Nintendo Wii, we all remember the game controllers that you can play tennis and so on. And so, as the years have gone by, we've become increasingly more sophisticated in the design of our sensors, and we've moved to much, into high value applications where they require the most demanding performance. So the 16545 really provides a performance and environmental resilience at a fraction of the size, weight, power, and cost of alternative inertial sensing technologies. And the accuracy and performance is now on par with some lower end fiber optic gyroscopes, but really coming at a fraction of the cost. And so we're really pushing the envelope of what MEMS can achieve.
And so what future enhancements or changes do you see coming down the line in the next few years?
Yeah, so we're actually continuing to push that envelope and in performance, size, and cost, which of course is important. And in the coming future, we'll see sensors that pack an even bigger punch, and kind of push the limits of what MEMS can do, and really compellingly encroach on the on the area now covered by fiber optic technologies, while offering a much different type of size, weight, and cost that allows applications to scale beyond what they can get to today.
Well, it sounds like exciting things are coming, so we'll keep an eye out for those. Thanks a lot, Zeno, for talking with me today about MEMS and IMUs, especially in relation to microwave systems, where our audience can appreciate that. We thank you for your insights, and we will catch up with you at a later time. For more videos in our audience, you can find them at videos.microwavejournal.com. Thanks for watching.